Alright, so hello and welcome everyone to week 12 of interactive live sessions for the course on Computational Fluid Dynamics for Incompressible Flows. The course is being offered by NPTEL. It's being instructed by Professor Amaresh Dalal from the Department of Mechanical Engineering in IIT Guwahati. I'm Debjit. I'm the TA for this course and I'm currently a PMRF scholar in IIT Madras. And like every other week, we shall be solving some tutorial problems together. So without any further ado, let's straight away jump into the questions. So we have question number 1 from today's session, which is asking us that for solving Navier-Stokes equations using FVM, that is finite volume method, what are the disadvantages of using a collocated grid? So there are four options given below. Read them carefully and try to pick out the correct option. So the first option is option A. Pressure difference between alternate grid points are taken. Option B. Velocity of cell center does not appear in the continuity equation. Option C. Wavy velocity or pressure fields are treated as constant fields. Or is it option D? All of the above. So in week 12 of lectures for this course, we have learned how to use finite volume method to solve Navier-Stokes equations. Now within that, there are two kinds of grids that we can use. There is collocated grid and staggered grid. Now this question is asking us what are the disadvantages of using a collocated grid. And there are four options given below. You have to select the correct one. So the option A says pressure difference between alternate grid points are taken. Option B says velocity of cell center does not appear in the continuity equation. Option C, wavy velocity or pressure fields are treated as constant fields. And option D says all of the above. That is A, B, and C, all of them. So which one would be the correct solution to this question? Let's have a look at the solution. The solution is option D, all of the above. That's because A, B, and C, all of them are disadvantages of using a collocated grid. So what happens is in collocated grid we have something like this. So this is our main cell P, and we are using these two neighboring cells, east and west, represented by E and W. Now while calculating the pressure difference across this, so I need the pressure at E and face small e and face small w. But when actually trying to do that, so delta P, that is PE minus PW, uh, we have to use, since we don't have the pressure values stored at the cell faces and only at the cell centers, we have to use interpolation between the two cell centers in order to get an estimate of that. So pressure P small e is taken as the average of PP plus PE by 2, and for P small w it is taken as PP plus P capital W by 2, and then ultimately we have something like P capital E minus PW by 2. So the pressure from alternate grid points are taken. So you can see E and W, these are alternate grid points. We are missing the intermediate point P. So that's why ultimately we end up using a coarser grid than the one that we have taken. So that is a wasteful way of doing things, and that depreciates the solution as well. So option A is correct. Now, option B says that the velocity of the cell center does not appear in the continuity equation. So, in 1D, if I try to do if I try to satisfy the continuity equation after integrating it, we will have something like, UEAE minus UWAW. In this case, instead of take since we don't have UE, we have to take an interpolation once again. So we will have to take something like U capital E plus UP divided by 2 using an interpolation like that. AE and AW are constant and equal to, let's say, whatever is the width of this. I'll call this delta Y. So this will stay outside delta Y. This is, so AE equal to AW equal to delta Y, just to make things clear. Now, UE is written like this and UW is written like this. And here also the P terms cancel out and we end up having UE minus UW into delta Y by 2. So here also you can see that in the continuity equation, when we are solving for the cell P, the velocity at P or any of its faces don't appear. The velocity at the two adjacent cells only come into the continuity equation. So that is also not a desirable thing to be happening. Then the last point, that wavy velocity or pressure fields are treated as constant fields. So this is something that we have seen earlier, known as the checkerboard field. So checkerboard pattern. So if we have something like this, let's say 20, 10, 20, 10, 20, it's a wavy pressure field like this. So in this case, when we are taking the pressure difference uh, between these 2 points, so for this point we will use interpolation and get 15. For this point also we will use an interpolation and get 15. So it ends up having no pressure difference between these 2 points. So that's why it doesn't matter whether it's pressure or velocity. Either way, it will end up being appearing as uh, any gradient free. It would appear as constant fields. So this is also another disadvantage of the collocated grid. So that's why we don't use it. We use staggered grids. And as far as this question is considered, all of them A, B, C are correct. So that's why option D would be the correct solution. Okay. Simple things. So we will move on. We will move on to question number 2 of today's session, which is asking us that for solving Navier-Stokes equations using finite volume method, what are the advantages of using a staggered grid? So earlier we saw the disadvantages of using a collocated grid. Now we are looking at what are the advantages of using a staggered grid. So is it option A? Pressure differences between adjacent grid points become natural driving force for velocity components. Option B. Differences of adjacent velocity components appear in the continuity equation. Option C. All of the above, that is both A and B. Or is it option D? None of the above. So read the question and the options carefully and try to figure out the correct solution for this one. So this is question number 2 of today's session, which is asking us that for solving Navier-Stokes equations using finite volume method (FVM), what are the advantages of using a staggered grid? Is it option A, that pressure differences between adjacent grid points become natural driving force for velocity components? Option B, differences of adjacent velocity components appear in the continuity equation. Option C, all of the above, that is both A and B. Or is it option D, none of the above? It is neither of A, B, or C. let's have a look at the solution. The solution is option C, all of the above, that is both A and B. So both A and B are correct in this case. So why? Let's have a look at that. So instead of a collocated grid, if I'm using a staggered grid, so if I have a cell like this for calculating the pressure, I will have a staggered cell like this, which is sort of shifted in the x direction, and in the center of that I'll be storing the velocity components. So as compared to this cell at E, U would be stored. So this is UE, and similarly, so the adjacent cell, sorry, uh, so this is cell E, this is cell W, and I have another staggered cell over here where I'm storing UW. This is small w point. Alright, so this is what we have. Now, the first statement or option that says pressure differences between adjacent grid points become natural driving force for velocity components. So I want you to focus over here for this cell. So here, if I am taking the pressure difference, that is PE minus PP, I have the exact value stored over there, so I don't have to use any kind of interpolation. These are the values which I have ready-made, sort of. So this becomes, so focus on this. I have a cell like this. I have the pressure here, PP, and I also have the pressure here, PE, and I'm trying to estimate the uh, velocity UE over here. So as far as this cell is considered, there is a pressure here, there is a pressure here, and the difference of that becomes sort of a natural driving force for the velocity UE within this small finite volume. So that's why the first statement, that pressure differences between adjacent grid points become natural driving force for velocity components. This is true. And this is the same thing in the y direction also. I showed in only one dimension. So in 2D, 3D also the same argument applies. Now, moving on to the second option or second statement, which says difference of adjacent velocity components appear in the continuity equation. So, for now, focus on this cell. So, for this cell over here, I have the UE, UW at this point, and I have the UE at this point. So if I'm trying to solve the continuity equation for this, both these will be appearing in the continuity equation. So I'll have something like UEAE minus UWAW equal to 0 being the continuity equation. So for this cell, cell P, uh, I have the exact velocities at the cell faces, and that's a much better estimate of the continuity equation for this particular control volume. So in 2D, similarly, I'll have the velocity components over here and here, right? So that's why this statement is also true, and since both of them are true, then option C, all of the above, would be the correct answer, and none of the above will not be the correct one. It will be incorrect. So that's why option C would be the correct answer for this case. Right? Now things are clear. We will move on. Give me a second. Okay. We will move on to the next question of today's session. We move on to question number 3, which says, what is simple method in CFD? Now, there are several options given below, different expansions of the term simple. You have to select the correct option whose abbreviation is simple, and that's actually the real thing that is used in CFD, the simple algorithm. So there are four options. Option A says semi-implicit method for pressure-linked equations. Option B, spectral implicit method for pressure-linked equations. Option C, simplex method for pressure-linked equations. Or option D, spectral implicit method for partial differential equations. So the simple algorithm, due to Professor S.V. Patankar, which is a commonly used method in CFD, even in industrial setting or a modern research setting. Uh, what is the full form of the simple in simple algorithm? Is it option A, semi-implicit method for pressure-linked equations? Option B, spectral implicit method for pressure-linked equations? Option C, simplex method for pressure-linked equations? And option D, spectral implicit method for partial differential equations. Let's have a look at the solution. It is option A, semi-implicit method for pressure-linked equations. Very simple. So basically, what happens is one of the velocity solving, or sorry, the momentum equations, it becomes something like this. So I have something like AP UP equal to summation of A and B U and B plus some source term. In that case, uh, this is actually dropped down to zero, and these are corrections, not the exact velocities, or rather the velocity corrections. So in this case, this term is dropped down to zero, assuming that this is zero. So some equation which was earlier implicit is now being approximated as something semi-implicit. So that's why the method is known as semi-implicit method for pressure-linked equations. Okay, simple. Now we will move on. We will move on to question number 4 of today's session, which is asking us what is the difference between simple and simple R method. So simple R is what? Simple revise, basically. The rest of the abbreviation is the same. So simple revise. That's where it gets the R from. Now, what is the difference between them as far as the algorithm or the methodology is concerned? So is it option A, simpler uses an additional velocity correction equation? Option B, simple uses an additional velocity correction equation? Option C, simpler is a fully explicit method? Or option D, simple is a fully implicit method? So read the options carefully. We have to determine the difference between the simple and the simpler algorithm. So option A says simpler uses an additional velocity correction equation. Option B says simple uses an additional velocity correction equation. Option C says simpler uses a fully explicit method. And option D says simple is a fully implicit method. So let's have a look at the solution. The solution is option A. Simpler uses an additional velocity correction equation. So what is done is that we start with some UV guess values. Then we determine the F stars, FF star rather, call this FF star. Then we move on to another equation in which FF hat is used, where U hat or V hat terms are used. These are something like, you know, the summation over A and B, U and B plus V. Similar to this, U and V both. Now, using these, the FF hat is used, and this equation is also solved. And then there is another pressure correction equation being solved. So, uh, Instead of solving only one velocity correction equation, we solve two in simpler. So that's why option A would be the correct one, because simpler uses an additional velocity correction equation. Okay, I hope that makes things clear. We will move on. We will move on to question number 5 of today's session, which is asking us what is the main advantage of using the simplex algorithm over the simple algorithm. So simple C now is nothing but another modification of simple algorithm, that is simple corrected. Sorry, I'll write the C in capital. Simple corrected. So that's where it gets its C from. It becomes simplex. So what is the main advantage of using the simplex algorithm over the simple algorithm? So there are four options given below. Option A says it can handle compressible flows. Option B, it is more accurate for incompressible flows. Option C, it is more computationally efficient. Option D, it is better suited for unstructured grids. Which one would it be? So question number 5 is asking us what is the main advantage of using the simplex algorithm over the simple algorithm? Can it better handle compressible flows? Is it more accurate for incompressible flows? Is it more computationally efficient? Or is it option D, it is better suited for unstructured grids? What is the main advantage of using the simplex algorithm? So let's have a look at the solution. Solution is option B. It is more accurate for incompressible flows. So what happens in simplex algorithm is nothing but this. So as we saw earlier, we have this equation APUP equal to summation of, sorry, these are corrections, UNB star plus B. Now in the simple algorithm, this term is dropped altogether. But in simplex algorithm, what is done is the U and B's, they are taken as the same as the UP prime, and then we have the summation of A and B over here. So left hand side remains the same. Now we do a little bit of mathematical manipulation and set this equal to B divided by so I'll take this term on the left hand side, then divided by that. So it will be AP minus summation of A and B. So uh, this offers a slightly more accurate estimation of UP prime, that is the correction of the velocity terms, and therefore for incompressible flows, using the simplex algorithm would give me more accurate answers. Okay, so that's it for this question. I hope that things are clear. We will keep moving on. We will move on to question number 6 of today's session, which is asking us that what is the purpose of the pressure correction equation in the simple algorithm? Is it option A, to correct the velocity field for the pressure gradient? Option B, to correct the pressure field for the velocity divergence? Option C, to correct the turbulence model for the pressure gradient? Or is it option D, to correct the mesh for the pressure gradient? Read the question carefully and try to figure out the correct answer. Question number 6 of today's session is asking us what is the purpose of the pressure correction equation? What is the purpose of it in the simple algorithm? Is it to option A, correct the velocity field for the pressure gradient? Option B, to correct the pressure field for the velocity divergence? Option C, to correct the turbulence model for the pressure gradient? Or is it option D, to correct the mesh for the pressure gradient? So let's have a look at the solution. The solution is option B, to correct the pressure field for the velocity divergence. So as we have seen in the lectures, the pressure correction term, this actually contains the velocity divergence term as well, in which I have something like this. So the velocity divergence, let me, yeah. So the pressure correction equation looks something like this. Yeah. So AP PP prime is summation of A and B P and B primes plus the source term, which is the divergence of velocity. This is coming from the continuity equation. This is nothing but the divergence of velocity. So I had some guess value of P star, and I'm adding this pressure correction to get the actual P. So this correction actually arises out of this uh, velocity divergence. So that's why option B would be the correct answer, saying that to correct the pressure field for the velocity divergence. Okay. So that is the main purpose of using the pressure correction equation in the simple algorithm. Okay. So we will move on. We'll move on to question number 7, which is a true or false type of question, which is asking us that in the simpler algorithm, pressure correction is performed after solving the pressure correction equation. Is it true or is it false? Very straightforward question, but make sure you remember the simpler algorithm properly while picking whether this statement is true or false. Okay, so let's have a look at the solution. The solution is option B, false. That is, even after solving the pressure correction equation, we do not correct the pressure. So in simpler algorithm, we do this in simple algorithm, but not in the simpler algorithm, where even after solving the pressure correction equation, not equal to, sorry, even after solving the pressure correction equation, we only update the velocity corrections using the pressure correction equation. So in this case, it would be something like u prime plus some factor f multiplied. It was dE as far as I can remember. dE pp prime minus. So I'm writing this for ue prime. So that is something like dE into pp prime minus pe prime. And there'll be an equivalent for the v velocity as well, that is in the y direction. and these are the only ones which are updated and not the pressure correction. So what we do is, after getting this, we again uh, solve for the actual value of p, and not the p is not solved as some p star plus p prime. No, this is not done in simpler algorithm. There is another pressure equation which itself is solved, and that gives us the better estimate of p, the pressure field. Okay, so that's what is done in simpler algorithm. So that's why the correct solution to this question would be option B, false. That is, in the simpler algorithm, pressure correction is not performed even after solving the pressure correction equation. So the pressure value is not updated with the correction. It's just solved, and then using those correction values, we correct the velocity corrections. Okay. I hope that makes things clear. We will move on. We'll move on to question number 8 of today's session, which is asking us that in finite volume method, if velocity at the boundary is known, how is the boundary condition handled? So is it option A, pressure gradient is set to 0, or option B, pressure correction gradient is set to 0? In question number 8 of today's session, the question is, in finite volume method, if velocity at the boundary is known, how is the boundary condition handled? Is it done by setting the pressure gradient to 0, or is it done by setting the pressure correction gradient to 0? Let's have a look at the solution. The solution is option B, pressure correction gradient is set to 0. So basically what happens is something like this. Let's say we have a cell boundary like this, and this is the cell. So it will be P, E, N, S, and instead of W, I'm writing B because this is the boundary, and the velocity over here UB is known. Okay. So it could be something like, in a channel flow like this, I can either mention the velocity profile over here, in which case all velocities at all the points in this inlet is known. Similarly, I can do a same thing like where the outlet is known. Okay. Another possible case is like at these two boundaries, at the walls, this one and this one. Here no slip boundary condition is applied, so I know the uv over here is 0. So here also I'm mentioning the exact value of the velocity at the boundary. So this case is similar to something like this, and this is a very common phenomena in setting up CFD runs in, you know in practical situations. So what happens, the flow coefficient, the flow term, let's say FB, at the boundary is something like FB star plus FB prime. Now, since I know UB, I know the values of FB and FB star as well. There is no need of this correction. This goes to 0. And in the finite volume method, this FB prime, this is something like minus delta y dB into rho b into the pressure difference. So pressure difference is something like uh, pp prime minus pb prime. Now, since this is 0, this is equal to 0. So the pb prime minus pb prime is equal to 0. And a similar thing would be valid at all, boundaries. So I can write this as the gradient of p prime equal to 0. So if velocity is known, if uv is known, then that is handled by setting the gradient of pressure correction to 0. So that's why option B would be the correct answer. Okay. I hope that makes things clear. We will move on. We will move on to question number 9 of today's session, which is asking us what is the correct sequence of steps in the simple algorithm. So there are 4 different steps, capital A to D are given. You have to arrange them in the correct sequence. So statement A is check for convergence. Statement B is solve the pressure correction equation. C, solve for the velocity field using the guessed pressure field. Option D, update the velocity and pressure fields using the corrections. And then there are 4 options given below, that is BCDA, CBAD, CBDA and ADCB. You have to pick out the correct sequence which is appropriate for the simple algorithm. So this brings us to question 9 of today's session, which is asking us what is the correct sequence of steps in the simple algorithm. The 4 steps given are option A or step A, check for convergence. Step B, solve the pressure correction equation. Step C, solve for the velocity field using the guessed pressure field. Option D, update the velocity and pressure fields using the corrections. And the different sequences which are possible answers to this question are option A, BCDA, option B, CBAD, option C, CBDA, and option D, ADCB. So we will have a look at the solution for this one. So it's option C, CBDA, that is the correct order. So first of all, we solve for the velocity field using the guessed pressure field, that is step 1. Then we go for solving the pressure correction equation in step 2. Then in step 3, we use those pressure corrections to update the pressure fields, as well as the velocity fields are also corrected. So that is step 3. And then finally we check for convergence. If it has converged, then fine. Otherwise we again move back to this you know step C, and using the corrected pressure field, then we solve for the velocity field again, and we keep doing this again and again until we reach convergence. So that's why CBDA is the correct sequence of steps which are used in simple algorithm. Okay, I hope things are clear. Now we will move on to the last question of today's session, that is question number 10, which is a similar question but for simpler algorithm. So this is asking us, what is the correct sequence of steps in the simpler algorithm? Sorry, please give me a moment. Yeah, okay, sharing has stopped. I'll reshare my screen. Yeah. So I hope my screen is visible now. This is question number 10, the last question of today's session, which is asking us, what is the correct sequence of steps in the simpler algorithm? Is it so there are 4 steps given below. So step A is solve the pressure correction equation. Step B is calculate FF hat and solve the pressure equation. Option C is solve for U star and V star and then calculate FF star. And option D, update the velocity field using the velocity corrections but not pressure. So this is something we saw earlier, that in simpler algorithm only the velocity field is corrected and the pressure field is not corrected. So these are the 4 steps A, B, C, and D, and then there are also 4 options given below containing different sequences. You have to pick out the correct sequence of steps. So the 4 options are option A, B, C, A, D, uh, option B, C, B, A, D, option C, C, B, D, A, and option D, A, D, C, B. So there are 4 steps given in this question. Step A says solve the pressure correction equation. Step B is saying calculate the FF hat and solve the pressure equation. Option C is saying solve for U star V star and then calculate FF star based on that. And then step D says update the velocity field using velocity corrections but not pressure. So let's have a look at the solution. The solution is option A, BCAD. So the first thing we do is we calculate FF star and we solve the pressure equation, FF hat, sorry. So we start with you know calculating U hat and V hat. I wrote down the formula for it in one of the earlier slides. You can go back to that, or you can go back to the lectures to have a look. And using them, I get FF hat, and FF hat is used to solve the pressure equation. That is step 1. Then we go to step 2, that is step C over here, where U star and V star, these are calculated these are solved using pressure. So using the pressure field that we got from FF hat, We use that to solve for U star and V star, and using U star and V star we get FF star. And in step 3, FF star is used in the pressure correction equation, that is step 3. And then finally, when I have the pressure correction, I'll use that to update the velocity corrections. So U prime and V prime, these are calculated using the pressure correction, but not pressure. Pressure is not uh, corrected, but rather pressure is solved for using this FF hat in again the when it goes back for the loop or iteration once again. So then the pressure is actually solved using FF hat. It's not corrected like I mentioned earlier. So the correct sequence of steps 1, 2, 3, 4 would be B, C, D, B, C, A, D. That is option A, B, C, A, D. Okay. I hope things are clear. Now, this was the last session for this course. Now, it has been a great learning opportunity from my side, and I gave my best efforts in making sure that it was the same thing for you too. Now, thank you all for joining during the entire course, and hope to see you again in another course. Okay, so with that, we will end today's session and uh, this course as well for this semester. Okay, thank you.